Hi, I'm Akash,
I'm Anirudh.
And I'm Shivangi.
and today we'd like to present to you Caesar, the Controlled Environment Agriculture System with automated recording. The global population is predicted to reach 9.7 billion by the year 2050. And to feed everyone, it's estimated that global food production will need to increase by up to 70% in the next 30 years. Now, conventional agriculture is going to be unable to meet all of these demands. The industry as it is today is highly polluting to the environment, and it results with food production with low nutritional value as well. The stats on the slide, for example, demonstrate these. 40% of Earth's land area is used for agriculture, and agriculture results in 5 million plus hectares of land being deforested every single year. The problem isn't just with environmental pollution alone. Conventional agriculture causes food production with low nutritional value as well. The reason for this is that agricultural food products are grown in rural areas which are located far from urban cities, which is where majority of the food consumption takes place. This means that food needs to be transported over very long distances to actually reach our plates. Now, scientific estimates suggest that approximately 30% of nutritional value in food is lost in just 3 days post the harvest. Furthermore, transportation results in the wastage of 30% of fruits and vegetables that are grown. These statistics are staggering and need to be solved right away.
Okay. Our solution is an environmentally sustainable and user-friendly system for growing plant indoors. Indoor vertical farms are the future of the world's food production, and as they are capable of producing the same output as traditional farms by using 98% less water, no pesticides, and a fraction of the land area. We present Caesar, Controlled Environment Agriculture System with Automated Recording, which is an energy-efficient and user-friendly system for growing plant indoors. Caesar aims to provide a low-cost method for monitoring and controlling factors that affect the growth of plants grown in indoor environments, including temperature, humidity, soil moisture, carbon dioxide content, and light intensity. Additionally, our system also incorporates a smart controller that identifies if the plant is diseased and optimizes further control actions to prevent the growth of such diseased plants in future. The growth of the plant and all the parameters can be monitored on an easy-to-use and highly user-friendly web application, which is coupled with a messaging service to alert the user of the actions being taken in real time. Caesar has 6 basic functionalities, one of which includes low-cost sensors to monitor temperature, humidity, soil moisture, CO2 content, and light intensity. The second aspect is the intelligent control system, which optimizes resources and conserves water. Third is the actuation system, which is autonomous and changes light intensity, moisture content, and ensures that the plant grows in a healthy way. Fourth is a web application that displays real-time data of the controlled environment. Fifth is an inbuilt messaging system to alert the user in real time of all the actions being taken. And sixth is our neural network, which has been trained to identify diseased plants and take appropriate actions.
Yeah. So our project comprises of 5 submodules, and it's all tightly integrated together by one backend server. Let's see all these 6 different modules one by one. The tech stack that we've used to build our app is based on a web application integrating with all of the different modules, as I mentioned earlier. To sense all the data, we're using an Arduino. To host the web server, we're using Node.js and Express.js. To store all the data, we're using PostgreSQL database. To render the front-end application to the user, we're using HTML, CSS, and React. Our code on the cloud, which is used for our image processing algorithm, runs with Python. And our messaging system is built on Twilio. The sensing system is all tightly integrated together by the Arduino Uno. We're using 4 different sensors to monitor 5 environmental parameters. The first sensor is a DHT22, which is used to monitor temperature and humidity content in the air. The second is an MQ135, which we've repurposed to act as a carbon dioxide sensor to detect carbon dioxide levels in the atmosphere in units of ppm. The third is a soil moisture sensor, a capacitive soil moisture sensor, which detects the soil moisture levels in the soil. And finally, we also have a BH1750, which we're using to measure light intensity. Now, it's important for us to measure carbon dioxide content because in indoor environments we can actually increase carbon dioxide concentration to enhance plant growth. In conventional agriculture systems, carbon dioxide content is restricted to just the parts per million that is present in the external atmosphere, and this can't be altered. In an indoor environment, we actually have the capability to increase CO2 concentration so that plants can grow faster. In fact, we can actually increase CO2 concentration from about 400 ppm in conventional farms to about 800 ppm, which is what we aim to do with Caesar. We're using a capacitive soil moisture sensor instead of a regular resistive one because of its longer endurance. It lasts longer and it also doesn't corrode when it's exposed to water. Conventional soil moisture sensors, resistive ones for that matter, actually erode and produce harmful chemicals into the soil as time progresses. So that's why we've chosen to go ahead with a capacitive soil moisture sensor. So here on the screen, you can see a real life demonstration, a depiction, an image of what Caesar looks like. The plants are grown in under exposure to red and blue, or also we could also say violet LED lighting, because plants are known to actually reflect green light and they don't use green light in their photosynthesis process. So to increase energy efficiency, we've actually not used any green LEDs. We've only used red and blue LEDs. We've also built a web application to actually show the user in real time all of the latest data that and the actions that Caesar has performed. So our web application runs on a Node.js backend, and this backend is hosted on the Raspberry Pi along with a PostgreSQL database. As the Arduino collects data from all the various different sensors, it actually sends the data to the Raspberry Pi via I2C communication. The Raspberry Pi collects all this data, and every time it receives data from the Arduino, it actually pings the web server so that the page refreshes, and then the user can actually see all the latest data in real time. Furthermore, every time the Arduino sends data over to the Raspberry Pi, it stores data in a PostgreSQL database. So when the user clicks on one of these environment cards that you can see on the screen, it pulls all of the data from the PostgreSQL database and renders it in the form of one of these graphs. Now, the front end of the application is built using React.js, which is a popular framework, open source. It's maintained by Facebook. So this particular framework, the front end of the application, integrates with the Raspberry Pi. In fact, it interacts with the Raspberry Pi backend through HTTP APIs. Whenever the front end requires some data from the backend, it sends an HTTP API request to the backend, and the Raspberry Pi processes this request and returns appropriate information back to the front end in JSON format. So the front end can easily interpret this JSON format and depict all the important information on the screen using JSON processing. The actuation system is controlled by the Raspberry Pi. So whenever the Arduino sends data over to the Raspberry Pi actually processes that data and understands whether the data is within some certain threshold or not. For example, if soil moisture levels drop below a certain threshold, the Raspberry Pi can activate a pump to irrigate the crop. Similarly, the Raspberry Pi can also activate the lighting system so that the lights are on for about 12 hours in the day and they're off for another 12 hours during the day. We've connected the pump to the Raspberry Pi using a relay module because the pump is a 12-volt system while the Raspberry Pi can provide only 5 volts. So the relay actually helps step down the voltage so that the Raspberry Pi can communicate and interact with control the water pump. Furthermore, we've connected the water pump to an external power supply because the Raspberry Pi is not capable of providing sufficient current to actually run the pump. So we've used a 12-volt adapter which is connected directly to the mains, and the positive leads of the 12 volts adapter and the pump are connected to the relay, while the pump is grounded to the mains using the 12-volt adapter. The Raspberry Pi can actually turn on or turn off the relay switch using some intelligent code, and then depending on that, the pump can turn on or off to irrigate the crop. The LED system is controlled directly by USB.
Now, moving on to the image classifier. Here we can see two images. One is a healthy one, another is an unhealthy one of an apple plant. So what the image classifier does is it trains on a data set of healthy and unhealthy plants which are labeled. So after the neural network is trained, it is run on a validation set, which is also labeled, so that we get to know what the accuracy of the neural network is. The neural network that we have trained for the Apple dataset is a 3-layered one. And upon running that with some test images, we were able to get correct accuracies. That is, we used a couple of unhealthy leaves and we got the output as 0. That is, we have used the label 1 for healthy and 0 for unhealthy. This neural network can be trained for different plants by just changing the number of layers, depth of the size of the layers, and also the learning rate. Here, we can see the cost function that we have used. And on the right, the graph depicts how the cost function changes per every 100 iterations. And we can see that it has reached a very low value, showing the accuracy, so showing the improvement of our algorithm. We were able to reach over 99% accuracy in both the training and validation data sets. So this image classifier will get real-time images from the system, and after which the neural network has already been trained on the data set. And then when given the real image, it will tell whether the plant is diseased or not, based on which the user can take real-time actions.
Coming to the user alert system, the system has been integrated with Twilio, which is a popular messaging service used for IoT-based applications. The algorithm scans through values of all the important parameters being received through serial communication, and once triggered, the API passes the incoming request to the central node, which sends the message to the authorized phone number and alerts the user. To work with Twilio, we created an authorization SSID and token, and it was used in the code. Since currently the team is working with a trial account and phone numbers of 2 members have been verified, following is a screenshot of the messages that have been received on the phone. So this was our solution to the problem faced in conventional agriculture, and thus we present to you Ceasar. Thank you.
Thank you.
Thank you.